Try to imagine the last number. Not a very large number, not a number with more zeros than there are atoms in the observable universe. The last one, the number after which nothing can be added. Hold it in your mind for a moment. Then add 1. The request collapses as soon as you obey it. Whatever number you choose, the mind quietly opens another door. 1 more, and then 1 more after that. Now try the same experiment with time. Imagine the final moment after which there is no later. Or travel in thought to the edge of space and place your hand against the boundary. What is on the other side? If there is nothing, does that nothing extend? If there is a wall, where does the wall stand? For some people, these questions feel playful. For others, they arrive late at night with the force of vertigo, the thought of time without a beginning, space without an edge, death as an ending we cannot enter in imagination, existence as a fact with no final explanation beneath it. The mind wants a boundary because boundaries make things graspable, but the moment it finds one, it asks what lies beyond. This is the strange human relationship with infinity. We cannot look at infinitely many objects. We cannot count through an endless sequence. We cannot store a completed picture of boundless space inside a finite brain. And yet, we can reason about infinity with enough precision to prove that some infinities are larger than others. So, what is happening when a finite mind touches an endless idea? Does logic carry us to the infinite? Or does infinity begin exactly where logic grows quiet? The first mistake is to treat infinity as an enormous object. Infinity is not simply the biggest number hiding at the far end of counting. There is no far end. Counting does not approach a final destination called infinity in the way a traveller approaches a city. It follows a rule. From any number, form another by adding 1. The rule is finite. The continuation has no prescribed endpoint. That difference matters. You do not need to imagine every future step in order to understand how the next step is produced. A melody can be generated by a short pattern, even if the pattern is repeated without limit. A corridor of mirrors can suggest continuation without presenting a final mirror at the end. A circle can be traced again and again without containing an infinite amount of paint. Our minds often reach beyond what they can display by learning a rule. Research on how people compare the infinity symbol with ordinary numbers gives this idea an interesting psychological edge. In controlled comparison tasks, people did not process the infinity symbol exactly as they processed 2 finite numbers. Their responses were slower. Their judgments also showed traces of ordinary visual and numerical magnitude, as if the mind were partly trying to place infinity on the same familiar scale as written numbers. That does not prove that the human mind cannot understand infinity. It shows something narrower and more useful. Even an abstract symbol can be pulled through cognitive machinery shaped by finite quantities, physical size, notation, and learned comparison. The symbol looks simple. The concept it points toward is not. Think about what your mind actually does when someone says forever. It does not display every future year. It may show a road fading into haze, a clock that never stops, or a loved one whose absence seems impossible to measure. These are finite images carrying an instruction. Do not place an ending here. The image eventually runs out. The instruction does not. No one sees every point on a line, yet a definition can specify the line. Understanding often depends less on mentally exhibiting every member of a thing than on knowing the relations that organise it. The mind does not become infinite in order to think about infinity. It uses a finite act to recognise an open structure. And this is where an ancient walk across an ordinary room becomes one of philosophy's most enduring confrontations with the endless. Imagine standing 10 feet from a doorway. To reach it, you must first cross half the distance. Then you must cross half of what remains. Then half again. Every remaining distance can be divided once more. So before you reach the door, it seems that you must complete infinitely many stages. Zeno of Elea used paradoxes like this to attack common assumptions about motion, space, time and plurality. If a finite journey contains endlessly many divisions, how can the journey ever be completed? Your body crosses the room without hesitation. Your description of the crossing appears to trap it forever. This is not just a trick with words. It exposes a conflict between two ways of seeing the same event. Experience gives one continuous movement. Analysis gives a sequence that can always be divided again. Aristotle responded by distinguishing what later came to be called potential infinity from actual infinity. A line is endlessly divisible in the sense that another division is always possible. But Aristotle resisted treating all infinitely many divisions as a completed collection that exists at once. The infinite, on this view, is not a finished warehouse. It is an activity that never runs out of another possible step. Modern mathematics gives us another tool. The distances 1/2, 1/4, 1/8, and so on form an infinite series whose total converges to one whole distance. Describing infinitely many subdivisions does not require the total distance or time to become infinite. That answers a central mathematical pressure in the paradox. It does not make every philosophical question disappear. A convergent sum tells us how magnitudes behave. It does not by itself settle what motion is, whether time is composed of instants, or whether a continuous event is literally assembled from completed static pieces. Infinity does not always silence logic. Sometimes it forces logic to become more exact about the question being asked. There is also a practical lesson hidden inside the doorway. The stages are endless, only because the description keeps subdividing the same journey. Your feet are not waiting for a cosmic accountant to certify each fraction before the next one begins. Motion is one event, and the infinite sequence is one way of analysing it. This is why language can manufacture paralysis. A task can be divided into endlessly smaller preparations, one more plan, one more revision, one more condition that must be satisfied before movement is allowed. The mathematics of Zeno does not diagnose procrastination, but the shape is familiar. We mistake an unlimited description of steps for an impossibility of action. The room is crossed, not because infinity vanished, but because an infinite analysis and a finite total are compatible. But the story turns when we stop dividing a finite path and begin treating infinite collections as mathematical objects. Imagine a hotel with rooms numbered 1, 2, 3 and onward without end. Every room is occupied. In any ordinary hotel, the word full means there is no room for another guest. But this hotel can accept one more. Move the guest in room 1 to room 2. Move the guest in room 2 to room 3. Move every guest in room N to room N+1. Room 1 is now available, even though no guest was removed. The hotel was full. The hotel made room. It can even accept infinitely many new guests. Move every current guest from room N to room 2N. All the even-numbered rooms remain occupied, while every odd-numbered room becomes available. The story is not proof that a physically infinite hotel could exist. It is an intuition pump for the behaviour of infinite sets. Rules that seem inseparable from finite collections can separate when infinity enters. The same shock appears when we compare the natural numbers with their squares. The squares are 1, 4, 9, 16, 25, and so on. They are only part of the natural numbers. Most natural numbers are not perfect squares. Finite intuition says the part must be smaller than the whole. But pair each natural number with its square. 1 pairs with 1, 2 pairs with 4, 3 pairs with 9. Every natural number gets exactly 1 square, and every square gets exactly 1 natural number. There is a 1-to-1 correspondence. Galileo saw the collision between these intuitions and concluded that ordinary relations, such as equal, greater, and smaller, could not be carried over so simply to infinite collections. Later approaches have tried to preserve the idea that a proper part should be smaller than its whole. George Cantor chose another path. He made 1-to-1 correspondence the basis for comparing the cardinality of sets. If the members of two sets can be paired without leftovers, the sets have the same cardinality. Under that definition, the natural numbers and the perfect squares have the same infinite size. That may feel like logic has betrayed common sense. A better description is that common sense was trained on finite collections. Cantor changed the rule for what answering how many means in an infinite domain, then followed that rule with extraordinary rigour. And then he found something even stranger. Not every infinity has the same cardinality. The natural numbers can be listed 1, 2, 3, 4, and onward. The integers can also be listed, even though they extend in a positive and negative direction. With the right arrangement, the rational numbers can be listed as well. Equivalent fractions can be reduced to one representative, so the same rational value is not counted again under a different spelling. These sets are called countable, not because anyone can finish counting them, but because their members can, in principle, be placed into a sequence indexed by the natural numbers. Now consider all the real numbers between 0 and 1. Suppose someone claims to have written a complete list of them as endless decimal expansions. Cantor's diagonal idea gives a way to construct a number missing from the list. Look at the first digit of the first number and choose a different digit. Look at the second digit of the second number and choose a different digit. Continue down the diagonal, changing one digit from each listed number. The new decimal differs from the first listed number in its first digit. It differs from the second listed number in its second digit. It differs from every number on the list in at least one place. So the supposedly complete list was not complete. The force of the argument is easy to miss because the construction is so economical. Cantor does not try to search beyond the end of the list. An infinite list has no final page to inspect. Instead, he uses the list against itself. Each row contributes the place where the new number will disagree with that row. Even if the first million entries were rearranged, the method would still produce a missing number. Even if the list were generated by the most ingenious machine imaginable, the diagonal rule would still answer it. The proof does not win by being faster than the list. It wins by exposing what the claim of completeness would require and constructing a contradiction from that requirement. One finite description, therefore, establishes something about an uncountable totality. We cannot print every real number. We do not need to. The proof reaches farther than enumeration can travel. The continuum of real numbers cannot be paired with the natural numbers in the same way. It is uncountable. In Cantorian set theory, it has a greater cardinality. There is not one mathematical infinity. There is a hierarchy of infinities. And for any set, Cantor's theorem shows that the collection of all its subsets has a strictly greater cardinality than the original set. There is no greatest cardinal waiting at the top. This is one answer to the episode's question. Can logic touch the infinite? Cantor's work says yes, if touch means define relationships, construct mappings, distinguish cardinalities, and prove consequences inside a mathematical framework. Logic did not arrive at the infinite and fall silent. It found structure where ordinary language had offered one blurred word. But that success does not end the philosophical dispute. Cantorian set theory treats completed infinite sets as mathematical objects. Finitists, constructivists, and other philosophers of mathematics question some of those commitments or insist on different standards for legitimate mathematical existence. The proofs can be rigorous, while the interpretation of what mathematical objects are remains contested. And just as infinity seemed to have been brought into a formal architecture, another question emerged. Could the entire architecture of mathematics be secured from within a single, complete system? At the beginning of the 20th century, David Hilbert's program sought, in part, to formalise broad areas of mathematics and establish their consistency through controlled methods. The aspiration was not irrational. It was an expression of confidence that mathematical proof could be organised on firm foundations. Then Kurt Gödel proved results that changed the boundaries of that project. To understand what those results mean, we have to resist the dramatic slogans that have grown around them. A formal system begins with a language, axioms, and rules for deriving statements. The rules are effective. A finite sequence can be checked to determine whether it counts as a proof in the system. Gödel's first incompleteness theorem applies to consistent, effectively axiomatized formal systems strong enough to express a certain amount of arithmetic. For any such system, there are statements in its language that the system can neither prove nor disprove. The second incompleteness theorem, under further technical conditions, shows that such a consistent system cannot prove its own consistency using only the resources available within that system. These are precise meta-mathematical results. They are not a declaration that all reasoning fails. They do not say every question is undecidable. They do not say no truth can ever be proved. And they do not prove that an unprovable statement in one formal system is unprovable in every possible system. A statement unavailable in one framework can be added as an axiom or addressed in a stronger framework. That stronger framework will then face its own questions. The boundary moves. It does not disappear. Imagine writing a new rulebook whenever the old one leaves a sentence undecided. The new rulebook may settle that sentence, but if it remains consistent, effective, and arithmetically strong enough, incompleteness returns at the level of the enlarged book. There is no suggestion here that every statement floats beyond proof. Vast regions of mathematics remain provable, useful, and stable. The point is that no qualifying formal system captures every arithmetic truth while preserving the conditions the theorem requires. This is not the same as saying that truth is whatever we feel. Formal truth and formal proof have exact meanings. The surprise is that they need not coincide inside one specified system. Nor does a human mathematician escape simply by noticing the theorem. We reason through assumptions, languages, social practices, and finite demonstrations. To convert incompleteness into proof of a supernatural mind, we would first have to establish claims about the mind that the theorem itself does not establish. This is why phrases like Gödel proved the soul or Gödel proved the mind is not a machine outrun the theorem. Arguments connecting incompleteness to human consciousness depend on additional assumptions, including assumptions about whether human reasoning is consistent and what it means for a mind to see mathematical truth. The theorem does not deliver those assumptions for free. It also does not prove mysticism, God, or a world beyond matter. Mathematical incompleteness is not an empty space into which any metaphysical conclusion may be inserted. What it offers is subtler and, in some ways, more beautiful. A rigorous method can reveal a limit without becoming meaningless at that limit. Reason can study the architecture of provability, distinguish what follows from which assumptions, and demonstrate that a particular formal ambition cannot be completed as originally imagined. A boundary discovered by logic is still knowledge. This is where the story becomes personal again. Human beings often experience a limit as humiliation. We want a final system, a final explanation, a final sentence that closes every question. If something remains undecidable, unobserved, or unrepresented, we are tempted toward one of two extremes. The first is despair. Reason has failed, so nothing can be known. The second is fantasy. Reason has reached a gap, so whatever we hope lies beyond the gap must be true. Neither response is required. An honest boundary can support a third response. Become more precise about what the evidence establishes, what the framework assumes, and what remains open. Immanuel Kant staged a related crisis in his Antinomies of Pure Reason. When reason tried to treat the universe as a completed whole, it appeared able to construct opposing arguments. The world must have a beginning in time, and the world cannot have a beginning. The world must have a finite extension in space, and the world must extend without limit. Kant's analysis belongs to philosophy, not contemporary observational cosmology. Some of his geometric assumptions were changed by later mathematics, but the pressure he identified remains recognisable. When thought tries to turn the totality of all possible experience into one finished object, it can outrun the conditions that would justify a claim. Modern cosmology gives us better measurements and more sophisticated geometry. It also gives us a crucial distinction. The observable universe is not necessarily the whole universe. It is the region available to observation from our location under cosmic history, not a demonstrated boundary of everything that exists. And a space can be finite without having an edge. The two-dimensional surface of a sphere is finite in area, but a traveller can continue without falling over a boundary. Other global shapes can also be locally flat while remaining finite through their topology. So measurements consistent with spatial flatness do not by themselves prove that the total universe is infinite. We do not currently know whether the universe as a whole is finite or infinite. The distinction sounds abstract until you imagine living on that spherical surface. Walk straight long enough and you may eventually return to where you began, although you never encountered a wall and never turned around. Finite does not have to mean enclosed inside a larger room. Edge and size are different questions. Now reverse the picture. A space may extend without bound and still have a geometry unlike the flat grid intuition supplies. Measurements made within our observable region tell us about local and large-scale properties we can test. They do not automatically disclose the complete global topology of everything that exists. So the childhood question, what is outside the universe, may contain an assumption the universe does not owe us, that the whole cosmos is an object sitting inside a larger container. The honest answer is not a more dramatic picture. It is to examine the geometry, the model, and the evidence before deciding whether outside is even a well-formed destination. Notice what happened. Mathematics expanded the menu of coherent possibilities. Observation constrained those possibilities. But the word infinite did not become an empirical fact merely because an equation permitted it. Logic can describe worlds that evidence has not selected. That is not weakness. It is the division of labour between model and measurement. Now, step outside on a clear night. The stars you see are finite in number. The light reaching your eyes is finite. Your field of view is finite. Your brain is receiving a limited stream of signals for a limited span of time. And still, the experience can feel larger than the self that is having it. Psychologists study awe as a response involving perceived vastness and a need to revise or accommodate existing mental frames. Research does not reduce awe to one universal effect. Findings vary with context, culture, methods, and the form of awe involved. But the central experience is familiar. The old mental frame feels too small for what has entered it. That feeling can become spiritual. It can quiet self-concern, awaken curiosity, or create a sense of connection. But awe is evidence that a human being is responding to perceived vastness. It is not proof that the universe is infinite. It is not a detector for metaphysical truth. Wonder deserves more respect than being used as counterfeit evidence. We do not have to choose between sterilising the mystery and pretending the mystery has answered us. The night sky can be emotionally transformative, while the topology of the total universe remains unknown. Cantor's hierarchy can be mathematically rigorous, while the ontology of mathematical objects remains debated. Gödel's theorems can establish exact limits on specified systems without turning every intuition into revelation. Humility is not the surrender of reason. It is reason refusing to claim more than it has earned. So return once more to the last number. You still cannot imagine it because every candidate permits another, but you now know that this failure of imagery is not the whole story. You can understand a continuation rule without completing the continuation. You can compare infinite sets through mappings. You can prove that one list cannot contain every real number. You can identify conditions under which a formal system is incomplete. You can distinguish a finite space from a bounded one, and a mathematical possibility from an observed reality. Logic touches infinity through relationships. It does not hold infinity like an object in the hand. It approaches through definitions, limits, correspondences, models, and proofs. It learns where a question changes meaning. It marks the point at which an axiom, measurement, or interpretation must be named. Perhaps understanding was never the same as possession. Perhaps to understand something is not to contain all of it, but to enter a disciplined relationship with it, to know what follows, to know what does not, to know which uncertainty is honest and which certainty is invented. Infinity does not begin where logic grows quiet. Sometimes infinity is where logic learns to speak most carefully. And beyond that careful speech, there can still be silence. Not the silence of defeat, the silence of a finite life standing before a question it can meaningfully approach without pretending to exhaust. Where does infinity first become real to you? In number, in time, in space, or in awareness? Share your answer below and subscribe to Soul Syntax for the next movement of Cogito Current.